This video will continue where we left off and start looking at advanced SIMD. Right, this change is a bit more tricky, hence the term advanced, I suppose. Basically, this is a representation of the current data layout. We just have the elements in the usual order. And we're going to rearrange them. So supposing we have a SIMD vector size of 3, what we're going to be doing is splitting the input into horizontal slices that each have a height, 3 equally tall horizontal slices, 1 per SIMD vector line. So because we have 12 rows here, we split them into 3 blocks, and then we rearrange it. So instead of like going this one, that one, then in the new data layout, we start with one element from block 1 here, then we take one element from block 2, one from 3, then we take the next one in block 1, and so on and so forth. So the new layout is kind of like visualized here. Now, the reason for that is, suppose we want to update this point. We have to load all of these neighboring values, and before, when we were updating, like we were updating 2.2 and 2.3 at the same time. So in this example, what was happening, the way I understand it, is what was happening is, for example, these two numbers, they have to be loaded once into a SIMD vector. Something like that, where they let me think about this, where they work as the upper left part of this value. Then these two have to be loaded. So notice that there's an overlap, and they have to operate as the center part for these 2 points, the upper middle part. And then these two have to be loaded, and they are the upper right for this part. So everything, almost everything here is loaded twice into separate SIMD vectors. So that's not very good. But with this data layout, what we are trying to do is we're trying to update this point and this point and this point at the same time. And the reason that is so much better is because then we are trying to load this point, and this point as the upper left, then this point, and this point as the upper middle, and so on and so forth. So because it's split up in this way, that we can, they all have the height of the SIMD vector, there'll never be any overlap, and we're kind of updating very distant elements. So yeah, so as I said, there's no overlap. That means that when we have this kind of layout and we want to update these 3 values, which is exactly what I said, 2.2, 5.2, and 8.2, 2.2, 5.2, 8.2, then we just load all of these SIMD vectors here surrounding them, and there's no overlap between any of the elements. So if we made the same kind of drawing with numbers, that would be kind of helpful, I think. Then you would see that there would have to be overlap on these central left elements, for example. Okay, so to make things easy in the update code, since we're already messing so much with how the data is laid out, we're also going to be adding zeros on either end, and then the corresponding values in here in the middle, which is a little bit more tricky to see how they work. But for this one, you need this point 31, and for this one you need 61, and so on. All right, so let's try to get started on that. So we want to update the data structure, and we need a few things. And I would like to just keep this old structure here and make a new structure that we call UV SIMD. And it's going to rely on this SIMD vector type that we define. like so. And it's going to be generic over the size of the instructions, which we don't really know. And we can put in a constraint that this size is actually a valid size. All right, so I think, and there we go. And it has 2 fields. So instead of being just some numbers, now it is SIMD containers, like so. All right, so let's start implementing this. Now we basically have to implement all of these functions we had before in a way that accounts for the new data layout and so on and so forth. So to further simplify our life, we're going to enforce that the size of the domain has to be a nice multiple of the SIMD width, so we don't have to think about edge cases and leftover things and like that. So we do it like this. It has to be divisible. And this one had columns. And this is another and. This is a modulo. So b width equals 0. And the message is num scalar rows, num must be divisible by SIMD width. Go. All right, and I think I will write out these details, and then if there's anything interesting, I'll restart the recording and we can talk through it. It's now actually several days later. I found a bug in the original code, which I ported everything and then I found a bug. I tried to implement this test that checked that everything was correct. But then I found a bug in the old code, and it's actually in the implementation that is in the course that we're kind of following. And what happens is that at the edges, the left and upper edges, I think is where the issue is going to be. The weights are actually not applied correctly, because if you look at this expression here, you have the stencil u, which is some u value you're looking at now, minus u. What is u? U is the center of the window. And that means that here, when I'm at the center of the stencil, it shouldn't matter what the weight is, because I'm taking the value, which would be u minus u. So it should just be 0. But if you run the old algorithm, you can actually see that depends on the weight. And that means that there's a bug, and it's, if you look at it, it makes sense actually. It's these edge cases that are not handled correctly. Now, the way we can fix up this code, I think, is just to do this. Then in the test, we don't really check the upper and the left edges. And now, if I'm correct, then this should work. It didn't work, and why is that? Why is that? It was actually something in the window. I had added something. So I think. Let me see again. 35. Oh, it's in the naive one, day 35. Yeah, here, what I used to test, that it was actually the case. All right, now we see something. Now we see still a small difference in the advanced SIMD. But funnily enough, it's actually at the other edge. So it's possible that we have yet another problem. So what we can do is, let's say we don't go all the way. We only test the inner part. So on the inner part, everything matches, but something is happening at the edges. And I think that the code is buggy. Here we are kind of zipping things. And if you think about how that works, it's definitely going to fail at the left edge. And it might also fail on the right edge, although I don't really see why it should right now. But anyway, I ported all the code. It's not that different. It's once you understand this this layout change here, where was it? Once you understand how this layout change works, it's kind of not so interesting. So I would recommend that you go look at that. Now let's add a benchmark. So let's first of all import advanced SIMD, and let's add it here. So change that to advanced, and there we go. Now this stuff has to be a SIMD with the SIMD layout. So we add that here. And now we have quite a big size. It has to be a multiple of 8, I think, on this machine. So that should work with 2048. And these guys, we just put something random in. Don't think I'm gonna do that for the SIMD ones because it's a little bit more tricky. What I'm just gonna do is say UV SIMD. Next time it's gonna be SIMD, and we'll just make a new. So it has some non-zero values in the middle. And that should do it. Here we just put MD here and there. And it's still complaining about something. Not sure what it's complaining about. It doesn't know the SIMD width, which is a good point. That is a good point. I'm not sure how to fix that. How do we actually call this? Well, we haven't, I don't think I ever got to that. So we don't really use it right now. Which means that we have to think about how we're gonna add it here. Here we use the vector type, just the SIMD type. So what I'm going to do for now in the benchmark is actually just say explicitly that it's 8. And then we're going to try to run the benchmark. All right, so here we have benchmark. Again, the naive update, 200 something, windowed 100, basic SIMD 50, advanced SIMD down to 16. It's pretty impressive. Now let's integrate it into our code. And what I would like to do is switch add UV SIMD. And I want to make another version of this function. Just gonna do this. And we're gonna say it runs with SIMD. And I think we're gonna have to have this function just be generic. And then these guys, they have the same SIMD width. And we need this, all this constraints and stuff. We need to include that. Like so. Put it here. We need to say it's okay to use portable SIMD, so we'll say that. And update function. Let's continue porting it. All right, so what's going to happen here? We're going to make a progress bar. That's fine. We can comment this guy. We need the concentrations to be the SIMD concentrations. So SIMD width, like, we don't need that. We can just do this, I think. And we, of course, we need to import it. Like this. And now we should be good to go. This one should be able to infer that the generic parameter is the same one as we have here. It was able to do. All right, so what we want to do is we want to say current v, and this is now an array view. So we also want to port this right to, no, it's a UE function, right to joined image. This guy, we wanna port that, and we're gonna make a new function that we call right array image. It's gonna take a path, or let's say it takes an array, which is the array view float. We need to import those things. There we go. Got a semi, got a colon like that. All right, so we have this right array. Turn some kind of thing. Okay, array that shape. Stuff. So if I have to dereference it like this. All right, whatever. And we are not doing 2 times because we're actually only writing one array. We saw before that they were actually the same like the patterns of the U and V arrays were exactly the same, just kind of flipped in color, so they were not really interesting. So what we're going to do here is we're going to say array and mutable pattern in local binding. What? Saying to me. Okay, we don't know because that's how it works. Anyway, let's say height is array shape 0 and width is that. Then we don't need to dereference things, and there we go. Now down here we say write array image. We take the array, which is concentrations, v, and the path. And we're gonna unwrap that. We don't have the path. We should say file name. And there we go. Now, how do we call it? How do we call it? So let's make one that we call start. Start SIMD simulation. And should take some options. And in this one, we do want this multi-version stuff. Think. Where did we have? We had some example. Guess it was here. And then we can specify, or we can figure out what the correct SIMD width should be. We need to import that. Put it here. And then we can say run simulation SIMD. And we use the same options. The update function is now going to be start. Okay, so actually we want the full options. I guess. So let's just say options. So start and end, what we're going to run is gray skirt, advanced MD, update, options.update, start and end. And here we're going to say failed somehow. Now this one needs some runner options. Gonna give it that, and let's give it the SIMD width here, and there we go. Now we are good to go. Now, in which case should we run this? So we need to add something here. Maybe that's the runner options. We want to do something like use SIMD. To be a Boolean, and it's of course an arg. The short one is let's use S. The long one is SIMD. The default value is maybe true. Now, if options dot runner that use SIMD, do one thing, otherwise we do this one again. And in this case, we want to say start SIMD simulation using the options. A reference to the options. So that should do it. I believe we have a data folder. So let me just remove that and make it again. And then we're gonna run this in release mode. And we will time it as well. But let's build it first and then time it. And then I will see you back here once the run is finished. All right, took about 10 minutes. Let's see the data, got a bunch of stuff. Let's remember how this one works. And we go into the data, I guess, and we kind of run this one. And it's created a video, which we can now check out. So here's the video. Let me rewind it. We have the initial thing here. Should be constant. Doesn't really look fully constant, but all right. And this is basically the thing we saw before. I can kind of skip ahead, I think. So it took 10 minutes, but I also think the simulation domain is quite a bit larger than it was before. So anyway, that's gonna do it for this video. And what do we have coming up? We have a little bit of stuff here, which we may or may not look at. I think I'll read ahead of time and decide if this is something we should go into. But until then,